Hello, future engineers. Welcome to my YouTube channel. If you're still new to my channel and you like what I'm doing, please don't forget to subscribe and share my videos to your friends and to your friends' friends. That's the only way you can help me promote my channel and to keep me going, refreshed, and inspired. And I'm very willing to share my knowledge, especially topics in civil engineering for your benefit. Determine the ratio of the plastic moment to the maximum elastic moment for a W 914 by 238 beam, steel beam with the following properties. So the moment of inertia with respect to the strong axis, which is the x-axis, is not given. So we will compute it and let's treat all these dimensions as solid rectangles. Then we have the second requirement to compute the above ratio if the moment of inertia is 4058 times 10 to the 6 mm to the fourth is given. So first, let's treat this as uh, the parts are component rectangles. So it will give us lesser value because of this fillet here, which fillets which are not accounted for in this actual moment of inertia with respect to the x-axis. So we expect that the moment of inertia by treating this as rectangles will be lesser than that. But if not even, we always treat this as rectangles to compute for the moment of inertia. So by symmetry, the elastic neutral axis will be this line here, which divides the area into halves, which is also the plastic neutral axis because of symmetry. So that's 305 to 25.9 for elastic action. The outer fibers will be subjected to uh, maximum stress, in this case sigma y. So that's 16.5 thickness of web, thickness of flange, then the overall depth 915. So half of 915 is 457.5 mm, and this distance is 457.5 minus 25.9, so 41.6. This is 2 times 41.6, so 863.2 mm. So moment of inertia is moment of inertia of big rectangle, 305 times 915 cube over 12 minus 305 minus 16.5. These two hollow rectangles times height 860.2 cube over 12. So therefore, I is 4007.53 times 10 to the 6 mm to the fourth, which is expected less than the actual moment of inertia as stated earlier. But that's just a small discrepancy because that's a lesser percentage. So sigma y equals m e elastic y over I, where y is 457.5 to the extreme fibers. So times 1000 square, assuming ME is in kilonewton meter, divide by moment of inertia 4007.53 times 10 to the 6. So ME in terms of sigma y, cancel out 1000 square and 10 to the 6 is equal to 8.7596 of sigma y kilonewton meter. Then for plastic neutral axis, the entire section will be subjected to sigma y as shown. So that's sigma y, that's also sigma y. So area above the plastic neutral axis equals area below the plastic neutral axis. So we just compute the moment arms. That's FC1, then FC2, we have FT2 and FT2. FT2, FT1 rather. So the moment arm between FC1 and FT1, because they are equal, is overall depth 915 minus half of 25.9 minus half of 25.9, or simply 915 minus 25.9. So that would be 889.1. While the distance between FC2 and FT2 is half of 41.6, half of 41.6, so simply 41.6 mm. So FC1 is equal to sigma y, which is equal to FT1, sigma y times area of the flange 305 times 25.9 divided by 1000 to convert it to kilonewton. So 7.8995 of sigma y. FC2, which is equal to FT2, is equal to sigma y times 16.5 times 41.6 divided by 1000. So that would be 7.1214 sigma y kilonewtons. Then the moment, plastic moment, is equal to FC1 times 0.8891 meter. So that it will be in kilonewton meter, plus FC2, 7.1214 of sigma y times 0.4316 meter. So plastic moment therefore is equal to 10.097 of sigma y. Therefore the ratio 10.097 sigma y divided by 8.7596 of sigma y. So 10.097 sigma y over 8.7596 sigma y. So the ratio of plastic moment to maximum elastic moment is equal to 1.153. Usually for this wide flange section, the ratio is between 1.1 and 1.2 in steel design. So that is inside the range, usual range for ratio of plastic moment to elastic moment. So always remember that. Outside that would be questionable ratio. Then recompute the above ratio if I is 4058 times 10 to the 6 is even. So sigma y equals moment elastic times 1000 to 1000 square to convert it to kilonewton to Newton mm rather. Y is 457.5 divided by actual moment of inertia. So cancel 1000 square and 10 to the 6. That would be 8.8699 sigma y, while the plastic moment of inertia remains the same. So MP over ME equals 10.097 sigma y over 8.8699 sigma y. So therefore the ratio is 1.138 or 1.14. This is 1.15, so it's very close. So that's it for this problem.